calculate the average velocity between 3 and 8. So now you know your interval is very clear between 3 and 8. And then finally, it's instantaneous. Calculate the velocity at t equals 2. So now you need to take your limit as h equals to 0. Any other questions from 1.3?
Miss,
Yeah.
I had a question about 1.2. So for question 22, for the horizontal line and finding the, I don't know, like the point, how would you solve that if it said it was a vertical line and the slope was undefined? Would you be able to solve that?
No, you can't.
Okay, no way.
No, no, you can't. What else? Well, I shouldn't say you can. You might be able to. If you know that the slope is undefined, you know the denominator is equal to 0. So if you just so happen to have a rational expression, you could solve for where the denominator is equal to 0. You could do that, and that would be a way to find it, but you won't be asked that.
Okay, thanks.
Yeah. Do you understand what I'm saying?
Yeah, because it's undefined, because it's denominator 0. Yeah.
Yeah, so it would be basically, you would solve it to where your denominator is equal to 0. But, yeah, like find out where your denominator is equal to 0. That's all.
Okay, thanks.
No problem. What was I doing? Yeah, tell me.
Can you do 1.3 number 11?
Yeah. Let's see if I have it. If I don't, I will do it. Right. Funny, it's always the same question. That's why we save them, because they come up again and again. Okay, so let's see number 11. The time in seconds taken by an object dropped from a height of s meters to reach the ground is given by the formula t equals radical s over 5. Determine the rate of change in time with respect to height when the object is 125 meters above the ground. So they're giving us the height. They're not giving us t. But if they give us the height, can't we find t? The time in seconds, come on, drop from a height s, yes, okay, to reach the ground is given by the formula. T equals. Okay, never mind. We've got t equals. We've got our variables interchanged. So now our formula, our independent variable is 125, and they gave us that, so that's fine. We don't need to solve for anything. So you're subbing into your equation 125 plus h over 5 minus radical 125 over 5 divided by h. And we notice that if I sub in h equals 0, my function is undefined. This won't work. I can't find the slope. And so what I do is I rationalize the numerator. So I multiply by what we call the conjugate. So the same terms as here, but the middle sign now changes. The middle sign becomes a plus. We do it in the numerator and the denominator because now I'm just multiplying by 1. Doesn't change what my expression equals. And we go ahead and we clean it up. So whenever we multiply two radicals that are the same, we know that it just comes out to be whatever's inside the radical. So for example, root 5 times root 5 is just 5. So root 125 plus h divided by 5 multiplied by root 125 plus h divided by 5 will just become this, 125 plus h over 5. And then here we have a minus. We don't have to bother with the middle term because the whole reason we did this was so that they would be 0, yes? So the middle term should be 0. And this, notice I don't expand it. And the reason I don't expand this is because I know that I want to cancel that h anyway. That's the whole reason I'm doing this. It's because I need to be able to calculate that limit. So I leave it out. And sure enough, you're left with h over 5 in the numerator divided by, just remember guys, this fraction line is just division. So you can rewrite it. You can rewrite this as h over 5 multiplied by 1 over this numerator. Okay, this is just division. And we end up with h over 5 times h in this whole expression. And now the h is canceled, and now you can take rid of it. Notice once I take my limit, I take away this. I don't have to write the limit anymore once I sub it. Then you're left with 150, what is it, seconds per meter? Yes, seconds per meter. So this one's a little bit different in the sense that we see time as a dependent variable, right, rather than independent, but otherwise pretty much Are there any questions? Anything else? No, we're good? Okay, so what I'm gonna do is I'm going to play that limit video. Was anyone able to find it? Was
Yeah,
anyone
I found it.
Yeah, were you able to play it?
Are you talking about the answers? Oh, the video. Never mind.
Kind of with the video, the calculus tool.
Yeah.
Yeah, you guys found
Nice
it?
one. Yeah.
Yeah, good, excellent. Okay, so I'm gonna play it for you. Another thing that I want to say, I gave you guys that website for Prep Anywhere. With Prep Anywhere, just be careful. One thing I must say, be careful. There may be an answer that's solved differently than the way we've learned in class. Just remember, when you guys are writing a test, any type of assessment, you must use the methods learned in class. You must use the methods learned in class, okay? So just be careful of that. Even programs or apps like Photomath, they do things very, very differently. And so if you're using Photomath, we can tell right away. And you're not necessarily going to get the marks because it's not the methods used in class. So be very careful because you will lose marks for that. Okay? You have to use the methods that are demonstrated in class. Okay. So let's get this video up and running. Let's see where it's at. Kylie never showed up, guys? Does Kylie show up? No. No problem. I'm just going to stop.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now, this might give you pause. You might think, how am I supposed to know? You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now, this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height. Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes height all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches the height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinate 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module.
So even though there may be a hole in a function, if both branches of the function lead to that hole, so they both go to the hole, then the intended height of that function is that value. And so the limit does exist. Okay? You can. You don't have to. You can. Okay, let's get to the next one.
Now you have some idea of what a limit is, and we need to talk about when does the limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the height from the right and the left are the same, then the limit exists.
So even if there's a hole there, doesn't matter. the two functions are arriving at the same height, even if it doesn't exist at that point, and so therefore the limit exists.
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4.
They don't arrive.
Let's go back to our dino metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal. Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrive at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the ground, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value. Once you can determine whether or not a limit exists, the next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the direction evaluate, basically you should be expecting to get a numerical answer. There are three major ways to evaluate a limit. They are substitution, factoring, and the conjugate method. We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that. Unfortunately, not all limits are this easy. You've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. The limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2 comma negative 2, and we concluded from that that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. We'll have to resort to this new method. We'll use the factoring method because the fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right. If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression. The square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression, which, as we said, is the square root of x plus 4. Now, the magic of this is that as we multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with the limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method.
Okay, so that's it. I don't need to fill it in. All right, so before we get started with the lesson, I want you guys to try this and let's see how you do with it. A little warm up. Right here. I want you guys to answer this question, please.